A particle moving in the xy plane has velocity vector given by v of t is equal to all of this business. And so using this notation, it just means that the x component of velocity is, as a function of time, is 1 over t plus 7. And the y component of velocity as a function of time is t to the fourth for time t greater than or equal to 0. At t equals 1, the particle is at the point 3, 4. So the first part is, what is the magnitude of the displacement of the particle between time t equals 1 and t equals 3? And then we need to figure out its position, and we need to round to the nearest tenth. So like always, pause this video, and I think you will have to use a calculator, but pause this video and try to work through it on your own. So we've done questions like this in 1 dimension, but now we're doing it in 2 dimensions. But the key is to just break it up into the component dimensions. So what we really want to do is let's find the displacement in the x direction, so really just the change in x, and then let's just find the displacement in the vertical direction, or our change in y, and then we can use those, essentially using the Pythagorean theorem, to find the magnitude of the total displacement. And also, if we know the change in x and change in y, we just add the change in x to the 3, and we add the change in y to the 4 to find the particle's position at time t equals 3. So let's figure it out. So change in x from t equals 1 to t equals 3, well, that's just going to be the integral of the rate function in the x direction from time equal 1 to time equals 3. So in the x direction, we have 1 over t plus 7. That's our x velocity as a function of time. 1 over t plus 7 dt. And what is this going to be equal to? Well, you might want to do u substitution if you're unfamiliar, but you might recognize that the derivative of t plus 7 is just 1. So you could think of this as 1 times 1 over t plus 7. And so we really can just take the antiderivative then with respect to t plus 7. So you get the natural log of the absolute value of t plus 7, and we are going to evaluate that at 3 and then subtract from that. It evaluated at 1. So this is going to be natural log of the absolute value of 10, which is just the natural log of 10, minus the natural log of the absolute value of 8, which is just the natural log of 8, which is equal to the natural log of 10 over 8, just using our logarithm properties, which is equal to the natural log of 1.25. So I can get my calculator out in a second to calculate that. Actually, I'll do that in a second. And then let's figure out our change in y. Our change in y, once again, we're going to take the integral from 1 to 3. That's our time, the time over which we're thinking about the change. And then what is the y component of our velocity? Well, it's t to the fourth dt. Well, this is going to be, take the reverse power rule, t to the fifth over 5. At 3 and 1. So this is 3 to the 5th over 5 is 243 over 5 minus 1 to the 5th over 5 minus 1/5. So this is equal to 242 over 5, which is what, 48.4? 48.4. Now let me get my calculator out for this natural log of 1.25. 1.25 natural log, and we'll just round to 2 decimal places, approximately 0.22. So this is approximately 0.22. So I figured out our change in x and our change in y, and actually just from that, we can answer the second part of the question first. What is the particle's position at t equals 3? Well, it's going to be our position at t equals 1, where to each of the components, we add the respective change. So we would add, so this would be 3 plus our change in x from t equals 1 to t equals 3, and it would be 4 plus our change in y. So this is going to be equal to 3 plus our change in x, well, that's going to be approximately 3.22, and 4 plus our change in y, that is what, 52.4. This right over here is 52.4. But we still have to answer this first question. What is the magnitude of the displacement? Well, it's the Pythagorean theorem. I'll draw a very rough sketch of what's going on. Sometimes it's useful to visualize it. So our initial position is at 3, 4. So 3, 4. So we're right over there. And we figured out our change in x isn't much. So our change in x is a positive 0.22. So our change in x, we're barely moving in that direction. And our change in y is 48.4. So we have a dramatic change. It really goes off the charts over here in that direction. But if we wanted to add them together, if we want to add those vectors together, you could shift over your change in y right over here, and then find the hypotenuse. The length of the hypotenuse would be the magnitude of the entire displacement. And so let's do that. So the magnitude of the displacement is going to be the square root of our change in x squared plus our change in y squared. Once again, this is just the Pythagorean theorem. And what is this going to be? I'll get my calculator out again for this. Okay, that was our change in x. Let me square it. And then plus, we are going to have 48.4. 8.4 squared is equal to this right over here. And then we take the square root of that. So this is going to be, let's see if we, right over there. And there you go. Our total, the magnitude of our total displacement is 48. If we round to the nearest tenth, 48.4. So this is approximately 48.4. And we're done. Now, one thing that you might be noting is, hey, it looks like our total displacement, 48.4, is the same as our change in y. Now, the reason why it came out this way is because our change in y was exactly 48.4, while the magnitude of our displacement was slightly more than 48.4, but when we round to the nearest tenth, we got to 48.4. The reason why they're so close is because our change in x was so small. We're talking about 0.22 as a change in x, and our change in y was so much that our hypotenuse was only slightly longer than our change in y. So that's why we got this result for this particular instance. In general, you're going to see the magnitude of the displacement is going to be larger than the magnitude of either x, our change in x, or our change in y alone.